Hello, everyone. I hope that you're doing great. I have the pleasure to present my feedback on porting a game to the browser, thanks to WebAssembly. So this talk is a mix of multiple topics. It's about WebAssembly. It's about some JavaScript APIs for multimedia. It's also about game programming and porting games in particular. So if you are like this, for you, porting a game development is something really difficult, really hard, or you don't even know where to start from. I hope by the end of this talk that you'll also get out and say, now I can also do it. Okay, so let's get started. So my name is Yassine. I am a DevRel at Worldline. I'm a teacher, have a PhD in computer science, and I'm also part of the Lille Android user group. It's an Android user group in Lille, in the north of France. So I'm part of a DevRel team in Worldline. So Worldline is a payment company, and we have some technical stuff to share. We have a YouTube channel. We have a technical blog. So if you're interested, please take a look. OK, so let me tell you my story by starting with a prologue, of course. So first of all, WebAssembly. Does anyone here know about WebAssembly, what it is? OK, some hands. Thank you. So quickly to explain, WebAssembly is a binary format. It's a portable binary format, meaning that it can run on multiple platforms. And the initial target or the initial platform is a web browser, meaning that your WebAssembly file, once you have one, you can load it from the JavaScript side or load it with JavaScript and run it on your browser. And initially, it was used to speed up JavaScript. So this is an example of a WASM file to show you that it's a binary format. It's like assembly, but more portable format. And you can have it in a more readable format using a tool that you can find on the internet. But the file is what you see on top. So what's really interesting in WebAssembly, what I want to highlight for this presentation, is its ability to port code to the browser. So suppose we have some source code written in C#, C++, or any other language that can be compiled into WebAssembly. You can then compile it to WebAssembly. So you obtain a binary in a WASM format, and then this file, you can load it from any browser that supports WebAssembly. All the modern browsers support it. And the JavaScript loads, from JavaScript, you can load this WebAssembly file and run it, meaning that you have access to another source or another language to execute code and to execute your business logic. And the WASM part and the JavaScript can interoperate with each other. For example, JavaScript can load information from the DOM, from the document, handle events, and pass the information to the WebAssembly code. It can execute, run the algorithms, and so on, and pass the result to JavaScript, and so on. So to summarize, WASM on the browsers allows to use a lot of languages, compile them into WASM, and run them on the browser. So that's a way to get to have access to more languages than JavaScript. And there is also the possibility to interoperate with JavaScript. So when I saw this technology, I told myself, I need to do something related to WebAssembly. It's very amazing. I haven't talked about WASI, which allows also WebAssembly to run on desktop. I haven't talked also about WebAssembly used for to implement the container technology similar to containers. So this is not the object of this talk, but WebAssembly is amazing by itself. So what I wanted to do, I didn't know yet what to do with WebAssembly until I heard about .NET and WebAssembly. So .NET is a cross-platform framework. Its language is C#. It's cross-platform open source, similar to the JDK. And .NET can run on many platforms. So as I said, Linux, macOS, Windows. You can make servers. You can make also applications, desktop apps, mobile apps. And until recently, or now it's starting to be a while, it can run on the browser thanks to WebAssembly. And one example is the Blazor framework. So it's a direct application of this WebAssembly support, meaning that your C# code can be compiled into WebAssembly and run on the browser. Blazor is an example. It's a framework similar to Angular, Vue, React. So it's a front-end framework where you write C# instead of JavaScript. The C# code is translated to WASM, and then it executes the business logic of your components. Initially, I did my work based on Blazor, but it was really complex, really intricate. So I switched to a new API, which appeared later, which allows to have more straightforward interoperability with JavaScript. That's what I'll show you now. Since .NET 7, you have a more straightforward way to communicate with C# with JavaScript. And you can see an example here. So you have a C# code and on the top and a JavaScript code on the bottom. So you see in C# code that we export, meaning that we make available to JavaScript a function. This function has been imported below in the area surrounded by the red square. This method is imported, and then we can execute it, or it's executed, and we get its return value. So this method has been called from JavaScript, which the JavaScript side called the method. The method is executed on the C# side, so on the WebAssembly side. And within that method, you will even find a JavaScript a method that requires to get it from JavaScript, because it's not available on the WebAssembly side. It's available on the DOM API. So not everything is available. Not all APIs, not all browser APIs are available to JavaScript to WebAssembly. But thanks to the interop, you can call JavaScript specific APIs from your C# code. So the get href is imported. So we have the import declaration below, and the export is on the JavaScript side, as you see on the bottom right of the bottom side of the screen. So this is the basic interoperability between C# and JS. So in this way, we can make a lot of things. Like we unlock unlimited possibilities. That's when I told myself, let's port a .NET game. I'm a gamer, video game collector. That's something that I really wanted to do. So I gave myself this challenge, let's port a game. But what game do I port? What game do I work on? So that's when came MangedDoom. But first of all, let's talk about porting games. So game porting means that making a game run on other platforms. It can be done in two ways. It's either with complete reimplementation on the new target platform. So we write the game from scratch. It takes time, but generally it's the method that gives the best performance, because when you build from scratch, you build to optimize on the target platform. Or the other porting method, which works well with sometimes better or worse results, which is to take a source code for an existing platform and just adapt it to work on the target platform. Many games have been ported like this, and generally the porting is done once we have a game running at a correct frame rate. And before considering making ports, myself, I thought that it was really hard. We need to be a very experienced developer in gaming. And when I saw this video from MVG, Modern Vintage Gamer, I don't know if you know this YouTuber on video games. So I really recommend to watch his videos. Really insightful, with some history, with some, even for developers, we can learn a lot of stuff. And during one of his videos, he explained how he ported A Heart of Darkness to the Xbox. And when I saw the steps, I told myself, we can do it. So the game that I decided to port was Doom. Why Doom? Because, of course, it's one of the biggest, greatest first-person shooters of all time. And also, because its conception, it's really easy to port. In fact, it's split into two parts. You have the logic part, which is called the Doom engine, where you have the AI, what is the update of the frames, the update of the frames, so how the enemies should move, how the character should move, the health points, and so on. So all the logic aspects are managed by the game engine. Even how to draw a screen, how to draw a frame is managed by the game engine. And all the resources, the music, the tiles, the sprites, the enemy, how they are drawn, the character, how he's drawn, the music, the maps also, the map data, everything is put into WAD file. So what does this mean? If you have a Doom engine running on your platform, you can run Doom games on your platform. You can run WAD files on your platform, and you have a port available. So Doom is portable by design. And there is a proof here. Doom has been ported to a lot of platforms. So these are some official ports of Doom, and they happen. So there are cartridges and CDs. I happen to have 3 of them on the left side, or on my left side. So Super NES, Game Boy Advance, and Nintendo 64 ports. There are even crazier ones like this, or more exotic ones, and there are even more. We can't count them. And for the anecdote, do you recognize the person here in the screen? Yes? Ah, yeah. So it's Bill Gates. So Doom was so popular at the time that he was in an advertisement for Windows 95, and he used Doom to showcase the power of Windows 95. And he was inside the advertisement, like he was shooting enemies and so on. And just for information, Microsoft bought ID Software recently, which is the company that developed Doom. So on my side, more concretely, I didn't start from scratch. It's game porting. So where did I start from? I started from, I started not from this. So there is the official source code of Doom published by ID Software. This source code has been ported to .NET on the desktop, which is by a GitHub user called Sinchu. He named his port MangedDoom, so you can play Doom on your desktop, thanks to .NET. But in this port, the graphic and the audio and the communication with the system is done through a library called SFML, which is a famous library for game development, multimedia development. Unfortunately, it's not available on the browser. So this library is not ported on the browser. So that's why I forked this repository and replaced all the SFML calls with browser APIs, or APIs compatible with browsers. And thanks to WebAssembly, I did this with minimal effort, or with less effort as possible. By the way, so the MangedDoom, so the code that I based my work on is currently, I used version 1 of this code. Currently there is version 2, but I wanted really to finish my work, my porting work, before thinking on switching to version 2. But the idea is the same. For example, they use another library called silk.net in version 2 of MangedDoom, but it's similar, like it's a library that just need to be replaced with native browser calls. So let's enter into more details about making the port. First of all, let's see what is a general game loop in a game code. So if you take C# or Java language, for example, if you want to develop a game, generally you will need to have a game loop in the main method, which iterates for every frame of your game. So if your game runs at 30 FPS, this loop iterates 30 times per second. If your game is at 60 FPS, this will iterate 60 times per second. And the logic is the same. You get the input of the player, and you send this input to the Doom engine so that it updates the game state, the character position, the enemy position, the health points, the current level. So all the state of the game is updated for one frame. And the result of this is is a frame and audio. So a frame buffer and an audio buffer. A frame, so a matrix, and audio, it's an array with audio samples. and then we render the frame and play the audio. So that's the basic logic of generally every video game. However, in JavaScript, there is a little difference or nuance, because in JavaScript, the doing like an infinite for loop is not really recommended, especially for games. There is a special API called request animation frame. So replace the for loop or the infinite loop with a recursive call and to a special function which itself manages its pace. So request animation frame, like if it's called like this, will only call itself 60 times per second. That's the standard frame rate for this call. So, and inside the recursive method, here we can call canAdvance_frame for frame pacing. If you want to do less than 60 frames per second, for example, if you want to do 30 frames per second, you can have a check to verify that your pacing is correct. And then you do the same. You get the player input, you update the game state, and so on. So that's first thing that need to be replaced in porting from .NET to JavaScript, to replace the for loop with this kind of loop. So let's dive a little bit more deeper into the port, how I made the port. So let's have a global, big picture view. So we have the game loop in C#. So we start from the C# code, which sends the input to the update game state, taking WAD and SF2, which is a sound font. You know, so in some video games, they don't have like the music in for each level. They have like sound fonts, basic sounds, and then they play with them or they modify them, combine them to generate music. Super Nintendo, Super NES also does this. It's called the sound font, which are like the basic sounds. So we give this into the Doom engine, and then he updates the game state for the frame. He generates an audio buffer and a frame buffer, which is rendered on the screen and played thanks to the SFML library. So, of course, this is iterated infinitely. And unfortunately, the first part and the last part are not available on JavaScript. But fortunately, 70% of the remaining C# code is immediately compatible with WebAssembly, because it's standard C#. There is no like specific APIs or APIs not available in browsers. So meaning that this port, 70% of the work is already done. So great. So what I did, basically, I replaced the loop with a request animation frame. So I'm on the JavaScript side, and then I do a call to .NET to update the game state by sending the input, which has been captured from the JavaScript side also. And and when the game state is updated on the C# side, we go back to the JavaScript side to play the audio and render the frame. So the audio is played with the audio context JavaScript API. And with the frame is rendered with the canvas, you know, the HTML canvas, which is a standard way of rendering games in the web. So as you can see, as you have seen here, it's a lot of travel from the JavaScript universe to the C# universe. So it's like a multiverse. It's a multiverse travel between two languages. So my porting strategy is to clone fork the repository and compile it. Like, just take the source code and compile it by targeting the browser, not targeting the desktop. And as long as I have errors, what I do is I put empty implementations when I find an error. Just continue until I have a build successful. Even if it does nothing, at least it builds. And little by little, implement using some guesswork, some logic. This is what we call reverse engineering. You know, that's also the funny part, in my opinion. Like try, guess, and fail, try and fail, and so on. And when I see that an API is not available in the C#, like I can't use it, for example, audio context and canvas, we delegate to JavaScript. So let me give you an example. So there is this class which comes from this class which uses, this class is part of the SFML library, which is called SFML sound. As you can see, the using it's SFML audio. This is not available in WASM. When you compile this by targeting the browser, you will get an error. So what did I do? I replaced everything with empty implementation. And then, like with some guesswork, I did something which reproduces the correct behavior. So a sound buffer contains an array and a sample rate, and this then, but the audio is not played here. To play the audio, we send it to JavaScript. So let's let's dive deeper into the code. That's why the screen will become black, of course. So this is the entry point of the game. Because it's a web app, the entry point is an HTML file. So you see the JavaScript file. This is the file responsible for loading the WebAssembly code and interoperating with it or interacting with it. And here we have our canvas. So all the rendering will be sent to this canvas. Inside the JavaScript, so the main JS, basically we have all the boilerplate code to initiate the WASM file, the .NET framework, and so on. And then we have the game loop that, as I showed earlier, which calls the update game state on the C# side. So this is a boilerplate. This is the update, the request animation frame, and this is the call to the C# side. And inside, so on the C# side, the update game state just calls the Doom engine, so the original implementation of the Doom engine, to update the game with the frame. So it advances by a frame. So inside the update game state method, we generate an audio buffer for the frame, like if there is a shooting, if the character shoots, or if there is a noise. And this audio is sent to the JavaScript. So how it happens? So this is what we call an audio wave. Audio is a wave, and then it is what we call sampled, meaning we take the integer value of the wave at regular intervals. It is called sampling. This sampling creates an array of audio values, which are then, these are all generated on the C# side by the Doom engine. And then we send this array to JavaScript, which then uses the audio context library to play this audio. And this is repeated each frame, each time there is a sound to play. This is how it's done, basically. So this is the code that does this. So you see at the top, we have the audio buffer, which is provided by the C# Doom engine. So we just send it to JavaScript. We delegate this to JavaScript. And this is just the boilerplate code to communicate between C# and JS. And this is the basic implementation on JS. So basically what we do, we load the library, we get the audio context, and then we create a sound buffer, and then we convert the audio we normalize the audio, because in JavaScript, the audio value needs to be between -1 and 1. And but the Doom engine generates value from 0 to, or from -max int to plus max int. So it's just a basic normalization. And then we send the audio to play it to the audio context. For frame rendering, Doom is really interesting because it uses a palette of colors. So you know that a frame, it's a matrix. So each pixel is a point in the matrix. But in Doom, in the Doom engine, it's a one-dimensional array, which is then converted into a two-dimensional array. In addition to that, each pixel does not contain the RGB value of the color, but it contains the index of the color index to another array. This is a technique used a lot in retro gaming to optimize space. To not have to rewrite every time 3 bytes of color for each pixel, you just need to have the index in the color palette. So in your opinion, can you imagine how the array at the top will be spread, or will be like put in the array, in the matrix? Can you try to guess how will it look like? Like, will the pixels go from left to right, top to bottom? So if you do this, you will get a weird image. That's what I tried in the beginning. Like I got, oh, it's ugly. In fact, Doom spreads the pixel like this, from top to bottom, and then from left to right. So yeah, that's That's, I think, the only moment that I read Doom documentation to understand how this works, or I tried really to like to understand how it works inside. But once you do this, the image works. So let me show you how it looks like in code. So the code that implements this is similar to the audio part. So somewhere inside the update state of the Doom engine, when the frame is built, we send it to the JavaScript side. So that's where you see render on JS. We send the frame buffer to JavaScript. And in JavaScript, you have a method which is called draw on canvas, which is at the bottom. And in the middle, you have like the glue that links the JavaScript to C#, that allows to JavaScript and C# to communicate. And draw on canvas, like basic, you get the canvas, you prepare the matrix, and you put the pixels one by one. So there is some bit shifting because so Doom gives the color in a color palette, but the canvas needs to get the RGB values. So we need to do the conversion ourselves. So if once we know the color of a pixel, we need to convert it to RGB values. That's why you see some bit shifting at the bottom to put the RGB values of each color. And for alpha, it's 225. There is no transparency. That's why the last line is always 255. So here's the code that puts the pixel from top to bottom and from left to right. So like basic for loop and basic bit shifting. And this is how we convert the color from the palette to an RGB color for the canvas. So now what I invite you to do is the demo, but you will do the demo. So please take your phones out, scan this QR code, and put your phone in landscape mode. Even if you have an iPhone, it should work. Last time I tested it, it was working on iPhone. So does it work? Or is it still loading, maybe? You can even switch, there are 3 WADs that are available if you... I'm hearing sound, so it works. Yeah. I'm hearing sound over there. Everyone, make some noise with your Doom games. Yeah, that's what we want to hear. Some amazing video game music, retro game music. So let me also show you on my side. So there is no audio, but it's okay. So you, as I said, so this is the Doom engine. You can play on your browser like this. And since Doom, you know, I said that Doom has a WAD, contains the resources and the engine handles the logic. You can find WADs on the internet, and you can replace a WAD, and you have another Doom game. You know, so this is free Doom. Let me load it. And here you have another Doom game, which is available for you to play. There is a button here which unlocks the FPS to the maximum for, the 60 FPS, which is the maximum for request animation frame. So you see that, like, for free, we get a game running at 60 FPS, 60 frames per second. It's not like the perfect port, which optimizes everything, no WebGL and so on, but it does the job. Like, we have 60 FPS game running very well. 30 FPS also works great. So that's what I mean by making a port by adapting a source code of an existing game. So next steps and conclusion. So the key takeaways. WASM possibilities are limitless, as you have seen here. So this is a really interesting way to use WebAssembly. I talked earlier about using implementing algorithms to assist JavaScript in terms of speed, containers and so on. And porting a game is a way to learn programming while having fun. So that's also a great way. I learned a lot of things thanks to WebAssembly, or thanks to programming games. So this is also another way to learn, is to program things that you love to do. And as next step, maybe I'll try to work on the V2 of MangedDoom, which is the latest version. Try to make it work on the browser. Thank you for your attention. This is the slide deck. You have the source code. So please enjoy, take a look and enjoy. Yes? Yeah, good question. So there are two things. The sound effects, so the gun, the enemy shout, and so on. This, when there is this kind of sound, I just get the audio buffer for the frame and play it on audio context. No special thing, because you know it's a short sound. But for music which is continuous, this is the most challenging part, because as far as I know, I'm not JavaScript expert, there is no way to, I haven't found a way to stream audio with audio context, like feed it with bytes and play along. So what I did is, and what I have noted is that if I play the music, like it's small bytes, small chunks every time, I hear a lot of noise, you know, a lot of cuts and a lot of breaks in the audio. So what I did is that since the sampling is 44,100 hertz, so I have like this, I build an array this big, and once I reach this size, I play it. So there is like a delay of 1 second in the audio, you don't notice it. That allows to play the audio without like glitches and so on. Yeah, I repeat. So when I have like 1 second audio, I play it. In the meantime, I prepare the second second, and so on. And with the audio context, when you have like the 1 second which is currently playing, not finished, and you have the next second which is ready, you can like delay the next, you can prepare to play the next, or cue the next audio, but you need to give it like when to start, you know. So there is some computation to know how many seconds are remaining and tell the audio context to play the second buffer after a certain time. Sorry? Yes, it's not very, very precise, but like for this kind of demo, it's not like very noticeable. Thanks for your question. Please don't forget to leave a review. And if you have any other questions, you can ask now or later. I'm here all the week. So if you have any question, please feel free to come to ask me. Thank you very much.
All systems are nominal. Initialize Genesis sequence.